Right, so today is topic 2 in our second unit on basically talking about limits. Limits were a topic that you hopefully watched a video for last couple of days, maybe yesterday. Limits are kind of a weird concept, though. The idea is try to figure out what something gets very close to but doesn't actually exist itself. And I promise you, there are purposes for limits. We will get to some more of those. But the basic idea, if I can just go back in the notes just to do a quick recap, is the idea, I need to do this properly here, is the idea that you might want to try to figure out what happens when x gets really close to a certain number. Now, sometimes you can just plug that number directly in. Like, for example, on this limit, which we did last day, you could just plug in 0 right here, because there's no reason why not. You could just go 1 over 0 minus 2 and discover that when x is getting really close to 0, it's getting really close to the number negative a half. But sometimes limits are more useful in a scenario where, for whatever reason, we can't actually literally plug this number in. Like, for example, in this one right here, the one non-permissible value is 2. And so if I want to figure out what's going to happen when x gets really close to 2, I actually can't plug in 2 because 2 doesn't work. And so, I mean, one of the first concepts we would do here is then we try to figure out, well, what happens if you tried plugging in 1.99999? And let's see what that gives you. Or what would happen if you plugged in 2.0001 minus 2? And in each of these cases, what you discover is that they might actually equal not the same number. This one right here, what ends up happening is this is actually getting smaller and smaller. This should be getting closer to negative infinity. And this one right here actually should be getting closer and closer to positive infinity. And therefore, for an example like this, because the left-hand bound, remember we did like little negative and positive notations up in the corner? The left-hand bound and the right-hand bound, if they don't converge on the same number, it means the limit does not exist. And even graphically, if you know what this graph looks like, this is going to be a graph that's going to have an asymptote here at 2. And it's going to look something like this. Do these graphs converge on the same point? Well, like, is this graph converging and landing at the same value? And they're not. No, this one's getting lower and lower, and then you have to lift your pencil off the paper, hop all the way up to the top. It's getting higher and higher, and so there is no limit for this particular one here. So that's a quick Cliff Notes review of what we should have covered last day. Today what we're going to work on is some laws about limits. And these will be kind of similar to how mathematicians have discovered that after they work with limits for long enough, they realize that there's some patterns to it. Similar to, say, like the exponent laws. You know, if I do 2 to the 2 times by 2 to the 3, that's going to be equal to 2 to the 5. And eventually we realized, okay, well, let's just make a rule about this that says 2 to the n times 2 to the m equals 2 to the n plus m. You know, we start putting some rules to them. So what we're going to work on today is to show you what the rules are. I'm just going to give you a list of them. And then hopefully after that, then we'll start using our limit rules to try to solve some questions here. So I've got some questions. After that, we're going to talk a little bit more about the definition of continuous. But before we get to that, let's start with our limit laws. So here they are. I'll just kind of read through them, and you can read them yourself. The first one basically works like this. If you have a limit that you're trying to work with for some sort of function, and there's a constant in that function, we've discovered that it's equivalent to essentially just pull the constant in front of the limit and not have to use it inside the limit notation. For example, and I'll do an example for each one of these that I can. If I were to ask you what the limit was for 2x as x approached 1. The answer basically here is that, well, you could just plug in 1 for x. There's actually no reason why you couldn't here. So you could just do the limit as x approaches 1. Basically, you're doing 2 times 1. 2 times 1 just gives you 2. But what you could have done, an alternate path, so rather than going this way, alternate path, is you could have done the limit as x approaches 1 for just like x. You could have put a 2 in front of it instead. And you can pull this constant out in front, which gives you 2 times, well, the limit as x approaches 1. I just wrote the same thing twice, didn't I? Is really the limit of 1 as x approaches 1. I'm not writing this very nicely. Do you see how this is going to be the same thing either way? Like, this is 2 times 1, and this is still going to be 2 times 1. It still ends up being 2. So it ends up being the same thing either way. So that's one of our first limit rules, is that constants really aren't affected. And the biggest reason why they're not affected is that x is not a variable that needs to get pulled in front. When you have 2x, you can consider, sure, this is all one term, but you could also consider it to be like 2 times by x. And see, when you're doing the limit as x approaches something right here, the x number gets put into this guy right here. X doesn't really need to get put into this 2 right here. That's not really relevant. So since what you're doing is you're substituting in a value in for this x right here, you may as well just substitute only into the x and not worry about the coefficient. So hopefully that made some sort of sense. I promise you it will when we do it in practice. Like in the actual examples, it's pretty easy. So here, let's do some more examples here. These will make intuitive sense. If you have the limit of 2 different functions that are being added, you may as well just have the limit of the functions being added separately, but have a limit sign for both. It's almost like you're distributing. It's not actually distributing, but in a way it kind of is. It's got some other properties. Similar rule here for multiplying. If you have 2 things that are multiplying, you can do the limit of each one of those 2 things individually. Dividing, similar thing for dividing. If you have an exponent, similar thing for exponent. Square rooting, similar thing there. So let's do some examples. This is probably the best way of answering these ones here, is we'll just use these rules. So right off the bat here, let's do the very, very first one here. The limit laws one's right here. Basically what this notation means is, well, let's see what happens as x gets close to 2. And unless you have a reason not to plug in the number 2, then just plug in the number 2. So literally the answer to this is 2. Well, that's it. That's all there is to it. I mean, if you want to consider this, there is like a 1 in front of it. So if you wanted to change this up, just to prove that other limit rules work, you could do limit of 1 times x, where x approaches 2. You could say that this is now 1 times the limit of x as x approaches 2. All of this just means here plug in 2 for x, because you can. So 1 times 2. At the end of the day, it's still 2. It doesn't really change much. Let's approach this from a different perspective. Let's look at it from a graphical perspective. From a graphical perspective, this is the function x, like y equals x. It's a linear line, y equals x, like this, right? Well, if I'm asking you for the limit as x approaches 2, what I'm really asking you for is, as we draw the graph from the left-hand side and from the right-hand side, as we come from this direction here, does it seem to converge on the same number? And yeah, I mean, as it converges on the number 2, right? When this is 2, this is 2. It's converging on the number 2. So all you have to do is plug that 2 in for x and get your answer. So on this one right here, really what ends up happening here is this is a constant term. I'm asking you, I mean, if you think of it from a graph point of view, let's start with that. From a graph point of view, this is the function y equals 3. So that's just literally a line right here. This is f of x equals x. This we're doing f of x equals 3. So if I give you a line of just y equals 3, what's it going to be as you approach from the positive and negative sides? Well, as you come this way and this way, either way, when x is 2, y is getting closer to 3. The answer to this one is just straight up 3. And here's another way of approaching it here. On this one here, when you took your 2 and plugged it in for x, that was logical. Here, plug it in for x. Well, I don't have anything to plug in for x, so I may as well not worry about it. Right? Now, using some limit laws, let's just show some other silly, but, I mean, this may seem strange. Why would you do it this way? But I just want to prove my point here. In a way, I could say that what we have here is the limit, and then my function is really, I have 0 x's plus 3. Like that's kind of another way I could write my function. There are no x's, and then you have 3 constant terms. Well, according to my limit rules, one of my limit rules says that I can separate these so that I can separate it into this guy and this guy here. Again, this is dumb. I don't know why you'd do this. But you could say, well, they're adding, so they can each have a limit there. I could even pull this coefficient out front and say, well, I could have 0 limits of x as x approaches 2. You could plug the 2 in right there, which sure would give you 2, but then it's 0 times 2, which means all of this goes away, which, I mean, again, this is silly because isn't this just what you started with? So back to the same point here, I'm asking you now to plug in 2 for every x. Okay, so I plugged in, I have a 3. That could even come in front. I could do the limit of, as x approaches 2. For literally there is no function right here. And I ask you, well, plug x into that function. Okay, well, I did that. I plugged x into the function. I mean, I didn't have to because there was no function remaining. So long story short, the answer to this is 3. So really, these two examples are a really roundabout way of me trying to illustrate two big concepts to you. When you're working with these limit rules, unless you have a reason why you cannot plug in the value as x is approaching it, literally, this just means substitute. So substitute in 2 for x on this one here. Now, if you don't have an x value, then whatever your coefficient is, that's just your answer. So let's try something a little more challenging now. Let's try working with this. Now, right off the bat, do I have any issues plugging in x being 1? Like, for example, if I plugged in 1 right here, is it going to cause me a problem? No. I mean, if it was x minus 1, I might have an issue, but we're good. But I want to show you how limit laws could work here. So even though this is really redundant, and we're only going to do this like once or twice, this could be equivalent to the limit as x approaches 1 for x to the 4 minus the limit as x approaches 1 for 4x to the 3 minus the limit as x approaches 1 for 7, all divided by the limit as x approaches 1 for x plus the limit as x approaches 1 for 2. Literally, I'm kind of using the rules right here. I'm using the division rule that basically says if you have the limit of two things in a fraction, the top one has a limit, the bottom one has a limit. And I'm also using this rule back here that says if you have two things that are added, you could limit each of them individually. So I'm kind of just jumping right to the point where I'm just going to limit all these things individually. And then I'm going to make one little change here to this guy right here. I'm going to use another limit rule on that one, where there was the first rule that says if you have a coefficient, you can just pull the coefficient out front. So if I do that, I could then make it 4 times the limit as x approaches 1 for x to the 3. Oh, well, then I'm just in this last step right here, all I'm going to do is just everywhere I can, I'm going to plug in x being 1. So right here, I'm going to plug in x being 1. It'll give me 1 to the 4. And then here, I'm going to plug in x to the 1. Well, that'll give me 1 to the 3. Here, I'm going to plug in what happens when x is 1. Well, there's not an x to plug in, so it'll just stay 7. Over here, I'm going to plug in x is 1. Well, it'll just give you 1. Here, I'm going to plug in what happens when x gets close to 1. There is no x to plug in for, so it'll just be 2. So my final answer is going to be 1 minus 4 minus 7, which is, I believe, negative 10. And then 1 plus 2 gives you 3. This is what happens in that particular function. When x gets close to 1, the limit gets close to negative 10 over 3. I mean, essentially, all I was doing is just plugging in a 1 for every single one of these numbers and seeing what you get. 1 minus 4 is minus 3, minus 7 is minus 10, 1 plus 2 is 3. I mean, you can kind of just go to this point here, but I want to show you how the limit laws kind of work as well, because we're going to need those in other proofs later on. So, okay, let's talk about then the next thing we can do with this. Let's talk about continuity. We have already kind of talked about what makes a function continuous in a couple of different ways. The first way was if you lift your pencil off of the paper when you're drawing a graph, it can't be continuous. Like, for example, this graph right here. So I had to lift my pencil to get from here up to here. That's not a continuous graph. If you have a hole in the graph and you have a graph that goes like this and there's a hole, that's not continuous. There's a gap. If you have, like, say, a graph that works like this and then like this, and there's like a gap in the middle of the graph, that's not continuous, right? So another definition we learned, though, about continuity was the idea that functions are continuous if you basically could directly plug this value straight in. That's a good definition of continuity. We've already talked about this definition here, where the function exists for the point you want to plug in, and the limit exists, and the quantities are equal, which means that as you approach from this side and you approach from this side, you're approaching the same spot. Okay. If you were to be approaching from this side and be approaching from this side, and you're approaching different locations. That doesn't work. So first of all, you have to be approaching there. There also has to be a point here. There can't just be a hole. But the point couldn't be down here while you guys are approaching here. The point would actually have to be there as well. That's continuity. So basically what we're saying here is that as x approaches a, if you can plug in a, that would be continuous. Okay. So let's try this example here now, because this is where things get a little more challenging. This is now a graph that's not continuous. The reason why I know it's not continuous is that I cannot plug in x as 3. Right? This fails my definition right here. Here it says the function exists when x is a. Well, if I'm going to try to pick this number here of 3, if I try plugging in 3, it does not work, because then I've got a 0 on the bottom. So what we can do here is kind of play like a little bit of a trick. And I've been talking with some of you as you do your assignments about how there's like a puzzle you're trying to solve here. Hopefully what you'll recognize here is that you can do the limit of the top and you can do the limit of the bottom. That's one of our limit rules, right? You can take the limit of each of them. And then if you wanted to, you could do the limit as x approaches 3 for x squared. You can do the limit as x approaches 3 for 9. You can do the limit as x approaches 3 for x. And you can do the limit as x approaches 3 for 3. And if you do the same process we just did here, this will give you 3 squared. That'll give you 9. This guy right here will just literally be 9. This guy right here will give you 3. Then you'll be minusing 3. You get 0 over 0. That doesn't make any sort of sense, because, I mean, it's not getting closer and closer to 0, I don't think. And second of all, you can't divide by 0 anyways. You got a problem. So I'm going to still use my limit rules, but I'm going to do some math algebra tricks. So try this instead. Before I start applying my limit laws, I'm going to do this very purposefully. I'm going to do some factoring before I even get there. So before I apply my limit laws, hopefully you'll recognize that this is x plus 3 over x minus 3. Right? Because that's the difference of squares on top. Hopefully you're familiar with that. Well, then that can cancel, which means that now I have the limit as x approaches 3 for x plus 3. Now, I mean, eventually we're going to stop writing this out because this is a little redundant to do this. But, I mean, technically what you're saying then is you have the limit as x approaches 3 for x, and you have the limit as x approaches 3 for 3. In this example right here, can you plug in x as 3? Sure, why not? Right here, you can plug in x as 3 if you want, but, I mean, there's nowhere to plug in the 3, so it's just the number 3. Long story short, this limit is 6. Now, if you try to, right off the bat, if you try to plug in 3 and 3 right here, you're going to see there's a huge issue because it originally gave us 0 over 0, but it actually ends up being 6. Right? And I want to prove this to you using a graph. Now, normally I'm going to say let's not use our graphing calculators. Your university classes will not allow them. Okay? But as a way to kind of confirm, just so that as we're learning through this, you can kind of hopefully get a more concrete picture of what's happening. I'm okay if we use them once in a while just for demonstrative purposes, but please do not rely on this as your way of solving. This isn't going to work. So if I were to graph this, I actually discover that this looks like a straight line graph, right? And that makes sense because hopefully you've learned about, well, if you factor and you cancel right here, I've turned this quadratic divided by a linear back into a linear, right? That makes sense. This looks like the graph of x plus 3. If I were to try to calculate the value when x was 3, if I tried to plug in 3 though, look, my calculator gives me nothing. I've got nothing to work with, right? However, if I try some numbers very close, like say 6.01, just slightly to the side, to do 6.01? That was dumb. I'm supposed to do 3.01. 3.01. Remember, x is approaching 3. It gives me 6, and a bit, just a bit above 6, but that's pretty close to what my limit was. And if I try the value when x is just slightly below 3, hey, look, that even said it was 6, right? But if you actually try to use exactly the number 3, 3 itself is not workable, but the numbers close to it are. So the limit is 6. Even though 3 itself is not a number you can use, we can still find that limit. And that's kind of what we're going to work on here, is trying to use our limit rules in conjunction with some algebra skills and basically the concept of substituting in the value to try to find what it comes close to. But we don't want to use a graphing calculator. That's not practicing the good skills we're going to need. So let's try this one. On this one here, what I'm really asking you to do is, well, let's plug in x as -4. Now, once you get fast at this, you could try plugging in -4 right there and -4 right here. But what you'll discover is that this guy will become 16. That'll become -28 with 12. If you try plugging in -4 on the denominator, it ends up giving you 0. So I can't really do that. So here's the work I'm going to want to see. Okay, so I've been going off book a little bit here on the previous examples. I'm going to try to do this example really nice so that you know what I'm going to expect on an assignment. So before you use your limit rules, what we could do before is we could factor. This would give you x plus 4, x plus 2, over x plus 3, x plus 4. Okay, so I'm not applying my limit rules just yet. I could in the future, but I'm not doing it just yet. The reason being is that I'm going to cancel the x plus 4s. I'm still got to keep writing my limit notation because I haven't actually plugged in -4 yet. And what I'm left with is x plus 2 over x plus 3. Well, according to my limit rules then, this could now be the limit as x approaches -4 for x plus 2. And it could be the limit as x approaches -4 for x plus 3. That's using the dividing rule. Then using the multiplying rule, this is the limit as x approaches -4 for x. And I've got the limit as x approaches -4 for 2. And I've got the limit as x approaches -4 for x. And I've got the limit as x approaches -4 for 3. Last step. If I want to do this one right here, when the limit as x approaches -4 for x, that just gives you -4. This guy right here is just going to be 2. This guy over here is going to give you -4. This guy over here is going to give you 3. So you're going to have -2 over -1, which means the limit was 2. Okay, this would be doing a really good job of showing your proof. Now I want to talk for a second here about some of the little details that I've included, and then I'm going to show you where you can skip a few steps. Okay. The first important detail, and I am really going to harp on this when I mark your assignments, is when you need to still have limit notation. So I have limit notation going on here. And when you're allowed to stop the limit notation right here. Okay. Once you substitute in your value of -4, once you plug that value in, you no longer need limit notation. But up until that point, you should keep writing that notation everywhere. So I kept writing it in all of these highlighted sections right here. But at this point here, once I plugged in -4 for x right here, like I did to get to these spots right here, and once I said, well, on this particular example right here, I can't even plug in the number, so it's just the constant term that remains, then you can skip the limit notation. So I do not want to see any more limit notation at this point right here because we've used it up. We've done our substituting. Okay, so I don't want to see that. The second thing I want to show you is that you can skip a couple of steps once you figure out the hang of it. So what you could have done at this point right here is you could have skipped all those limit rules and recognized where this was going to go, and you could have taken it straight to -4 plus 2 over -4 plus 3. Notice I didn't write the limit notation anymore because what I did is I plugged the -4 in for all of my x's. And I did that knowing that it wasn't going to cause me an issue where I'm dividing by 0. If it was going to cause me an issue dividing by 0, then I wouldn't have done that. I would have had to find another trick, right? Because if I try to do that up here, if I try to plug in my -4 at the very, very first step, it actually did give me a 0 on the bottom, which I can't deal with. So you can plug in the number from the limit once you get to a reasonable point. The question is where you get there, when you get there. So I would expect good-looking work then, if I want to kind of erase this and show you what my expectations would be, to look something like this. Something like this. I wrote out the first step. I factored, clearly showed that I factored. Still have my limit notation right here because I haven't substituted yet. I recognize that there is no issue anymore with me plugging in the -4 for x. I don't really need to separate it and write the limit out 4 different times. It gets a little ridiculous. So I plugged in the -4. At this point here, I don't write limit notation anymore because I don't need it anymore. I found my answer, and then I did a quick summary by saying, okay, well, all of this that I started with, this equals 2. Now, I don't want you to just write this as your answer in your work. If you just do this and you don't show me all this work here, I will not be able to give you credit. Because what I don't want you to do is take your graphing calculator, because you could do this. Take your graphing calculator, type in the graph right here, type in, find the value when x is like 2.001, and find out what it's close to. Keep in mind, this is not the same function, by the way, right? I don't want you to do that because that's not using the algebraic skills I want you to be working with. So don't just tell me that it equals 2. I want you to show me all the work and then summarize for me. Okay. Like I've been saying as we go through videos, make a list of questions, right? Things that you can ask me Tuesday, Thursdays, or whenever it is that you ask me questions. Rewatch the video, rewind, look at this again. So that when we need to on Tuesday, Thursdays, we can chat some more. I don't necessarily do a lot of wait time in the videos because I'm going to try to condense these down to 45 minutes or so, or less. So rewatch that if you need to. But I'm going to move on to the next example and try this one. And I'm going to go a lot faster now. So now that I've kind of done the basics, I'm going to go faster. So let's do this example. I could try to plug in 1, but first thing I notice, if I plug in 1, not doable. So I'm going to use either some limit rules, or I'm going to try to factor. Now, as I try this one right here, I realize that this one is a typo. This one is a typo. This should be a minus sign. Sorry, can you change that? It's supposed to be a typo, otherwise it defeats the purpose of the question. Okay. On this one right here, what we'll discover then is that x squared minus 1 really can be written as x plus 1, x minus 1. So rather than writing it like that, I should write it like x plus 1, x minus 1, all over x minus 1, which means you can cancel that, which gives you the limit as x approaches 1 for x plus 1. Now I could write the limit for both of these individually, or rather than doing that, I can now substitute in 1 for x, so I'm no longer going to write in my limit notation. By the way, sometimes it's nice to write equal signs here, just to kind of keep this straight. And I'll just substitute x with 1 and say 1 plus 1, and say that this is equal to 2. And so now I could write and say that my limit as x approaches 1 for x squared plus, no, we changed that, x squared minus 1 over x minus 1 is actually 2. Even though I couldn't plug this one in, I found the limit was 2. Quick check. Again, not normally going to do this, but if you want to do a quick graphical check, x squared, let's make it the minus 1 version, divided by x minus 1. Here's my graph. If I try plugging in a value close to 1, like say 0.99, it gives you 1.99. That's getting pretty close to 2. Now, I think the reason why I actually gave this question, or put this question on here, now that I think about it, is I actually did want you to do x squared plus 1, which the reason why I paused for a second and hedged is because I was thinking, hang on, you can't do it. But that's actually the point of the question. If I asked you to do x squared plus 1 over x minus 1, I can't factor that. I can't cancel something away. Okay? Let's see how this graph would change if it was x squared plus 1 over x minus 1. Let's say I tried this. Let's say I tried plugging in 0.99, something really close. Negative 198. Okay, so I might think, hey, my limit is supposed to be equal to negative 198. But I really should try it from both the positive and negative side. Think of a continuous graph. I should try it from both sides as the two graphs converge, so they converge on the same number. If I try the number 1.01, it actually gives me positive 202. Those are not converging on the same number. So I'm hoping that you'll see here that the answer for this one is that the limit does not exist. It's that whole concept that actually there is no limit for this one here. So I think that was actually what I was originally going for on this question, but this was a good learning tool to talk about how if it was a minus sign, the limit did exist because I could do some work. And over here, there's no factoring I can do. Even if I guess and check some numbers, it's not possible. Okay, let's try this guy here. This is kind of the point of where we're getting here, is that we want to combine what we did in our first unit on the pre-calculus stuff with this one right here, and combine some skills. What we're looking to do here is we want to plug in 2, obviously, right? But you'll discover that I can't plug in 2. So a lot of kids, they'll just default and they'll say, well, hey, the limit does not exist. But that may not be true. We need to actually try a few more tricks up our sleeve. So like I've been saying to a couple of you as you're going through assignments, you're looking for that light bulb moment, that aha moment when you get to it and you go, I see what you were doing there. You were trying to see whether I could solve this puzzle. And if you solve it, you will hopefully see, oh, you'll have this an epiphany where you'll go, I know that I'm doing it right. And you'll see that on this one if you do it right. I'm going to play a trick here. I'm going to multiply by the conjugate. I'm going to multiply by x plus this stuff here. So there. I haven't actually changed the equation because I'm just multiplying by the same thing on top of each other. Now, I have to be diligent. I have to write down the limit as x approaches 2 the whole time. If I don't do that, it means that I don't have the ability to plug in 2 later. So if I do this, I'm going to end up with x squared when you times the x by the x, and it's going to be minus 3x minus 2. Actually, it'll be 3x plus 2. Hopefully you caught why it's plus 2. It's going to be minus the 3x. It'll be minus, but like 3x minus 2 should really be in brackets. So when you distribute the negative sign, it's actually going to involve a plus there. Hopefully I didn't lose you there. This would be a good time to, if I lose you, write that down as like a good question to ask me later. I can elaborate on it. On the bottom, I'm still going to have this x plus that little mess over there. That's not really nice. And you'll still have the x squared minus 4. Kind of like bracket that up. Well, hopefully you'll realize that I can now do some factoring. The top of this thing ends up being x minus 2, x minus 1. The bottom of this thing becomes x minus 2, x plus 2, and then the remaining bit is going to be the x plus root 3x minus 2. Now, I say this a lot to my students, especially when I have them in person. Think about what limit notation means. It means plug in x being 2. And we try to, except for situations where we're not physically able to because we know in advance it's going to cause us to say like divide by 0. But here I'm going to cancel my problem away. I have to use that phrase. I'm going to cancel my problem. See how this guy right here is my problem? Hey, my problem is now gone. I no longer have an issue with this anymore. Because now when I want to do the limit as x approaches 2, the remaining bit is x minus 1. Well, there's no problem with me plugging in 2 there. And then x plus 2 and x plus root 3x minus 2. I don't actually see a problem anymore with trying to plug in 2. So note, though, I'm still writing my equal signs. I'm still writing my limit notation. Now I'm at the step where now I'll plug in what x is. X is really getting close to 2. Let's plug in 2. There's not a problem anymore. 2 minus 1 over 2 plus 2 times by 2 plus 3 times 2 minus 2. Well, the top is 1. That guy's going to be 4. 3 times 2 gives you 6. Minus 2 gives you 4. When you root 4, it gives you 2. 2 plus 2 gives you 4. Long story short, our answer is 1 over 16. And hopefully you have that epiphany moment right about here where that light bulb goes on. And you're like, whoa, I just realized something. Light bulb moment. Right? Where you all of a sudden realized This was the point of the question. The whole trick behind it was to see what you could get here. Because a lot of kids, they just give up and they say, there must not be any limit. I tried to plug in 2, I couldn't, I quit. Right? But you've learned, hopefully over the course of your math career, a whole bunch of different math, algebra tricks or maneuvers, or I guess I should just say you have algebraic ability. You need to utilize that to see what you can get out of it. Because yes, sometimes there will be no limit, but you can't just give up on it. Okay, rewind that, watch it again if you need to, write it down as your list of questions to ask if I lost you somewhere. Let's move on. Let's try this one. So, right off the bat, I want to try to plug in 3. I can't. Okay, well, let's play a trick. If I play a trick and I multiply by the conjugate, let's see where it takes us. I'm going to stop narrating for a while and just write. So if I lose you, make a note here. Watch double negative. All right, I got to pause here and comment a bit on what I did here. First of all, you got to make sure you watch that double negative, right? When you distribute and FOIL this out, x times x will give you x squared. The root x plus 6 and the root x plus 6 would give you x plus 6, but it's supposed to give you like negative x plus 6. Don't forget to distribute that negative and make that double negative, because if you didn't do that properly, this would not have factored to this guy right here, because this is your epiphany, your moment of zen, where you're like, I see the point of the question. It was for me to cancel that x minus 3 because now I no longer have a problem. My problem is, as I'm currently writing, that x is supposed to be 3. Right here I couldn't plug in 3, but now what I have left, I have no issues with plugging in 3. So let's do that. Now I don't need my limit notation anymore. 3 plus 2 over 3 plus that is going to give you 5 plus 3 plus root 9. Which will give you 5 plus 3 plus 3. Our final answer, this is getting close to 5 over 6. If you were to graph this thing, I don't know what it looks like, but probably somewhere in there's a hole in the graph. If you come from this perspective and come from this perspective, the point that doesn't exist on the graph is 3 with 5 over 6. If you tried to plug in 3 right here for x, it doesn't work. But it sure is getting close to 5 over 6. And we're finding where that hole happens to be. Okay, let's try this guy here. This is kind of leading into, this is our last example. This is really leading into our next set of notes, where we're actually going to use limits to do something a little more purposeful. Right now, you might be asking yourself, why are we doing this? I mean, part of it is just for the sake of doing it. I mean, I won't lie to you. First-year calc courses are really designed to thin out the herds and weed out kids. I think I already told you a story about how I emailed one of my old professors, and he told me that like the failure rate or the dropout rate in first-year calc is about 50% nationally, not just at the U of L. So like 1 in 2 kids doesn't make it through. Really, the whole point of it is to try to weed out kids for those professions who need calculus. Not because you use calculus, but because they're really trying to figure out who has the perseverance and the drive and the desire to stick it out in order to go into engineering or dentistry or medicine. So part of it is just it's hard for the sake of being hard because it's their filter. It's their way of figuring out who gets to go on and who doesn't. But I promise you, limits and calculus, they do actually have uses in everyday life. Like, people do use this stuff. Maybe not every single day, maybe depending on the career, but this is useful. And so anyways, the point I want to make is that this last example is going to lead into tomorrow's lesson, or whenever you watch the next video. It's going to lead into the next lesson. In terms of what we're going to do, we're going to use limits to find tangents. That's actually tomorrow's topic. So this is kind of a good precursor to it. So let's try this last example. I want to try to solve this one right here. As what I discover is that I want to try to plug in 0, and I can't, right? Because if I plug in 0, I've got a problem. So I got to do a little bit of work. Now, I don't have a unique trick like I did last time where I multiply by the conjugate. Right? That's not going to actually happen because there's no conjugate here. That's not going to solve my problem. But I'm just going to just go with the flow. I'm just going to FOIL this bit out here. Because if you FOIL this out, it'll give you h squared plus 4h plus 4. If you FOIL this bit right here. And then, hopefully what you'll discover, this is your moment of Zen, this is your epiphany right here. 4 minus 4 right here will actually cancel, which will leave you with h squared plus 4h over h. Now, I'm still stuck. I cannot plug in h as 0 because of that h right there. But, look at the top, you can factor it. I can factor out an h. And the reason why that's worthwhile is, again, another epiphany moment where you go, wait, I see where you're going with this, Chris. I see why this question has been designed this way. They're not designed randomly. They're designed very purposefully because, look, this h cancels. I have now canceled my problem away. My problem was that I had an h on the bottom that I couldn't plug in the 0 for, but it's gone now. Now, can I plug in that? Sure. I mean, if I really wanted to, I could use my limit rules and say this is the limit as h approaches 0 for h, plus the limit as h approaches 0 for 4. But, I mean, really, this is 0. This is 4. So my answer is 4. Notice that I got rid of my limit notation now, right? As soon as I started substituting in the 0, I'm done. So there, I've now actually solved it. The answer is 4. Now, I can't plug in 0, right? On this graph right here, if this was a function, 0, 4 is not actually a point, but there must be like a hole in the graph, and that hole in the graph would be at 0 and 4. So that's kind of it for my lesson today. If you get a chance, watch the next lesson more or less right away as soon as I have a video posted, if possible here, because this is meant to lead into our next topic. We've kind of finally got to the point of calculus, which is that we're going to do something with this. We're not just doing this just for the sake of doing it, just because it's hard, just because we need to weed you out of your calculus courses. Our next lesson is going to be on trying to do something purposeful. This is going to be using limits to find tangents. And yeah, I'll start making that video when I get a chance, and hopefully you can watch that one. So just to sum up for the day, if you have questions, hopefully you've been writing them out on a list. Make sure you email me. Please email me all the time. Check your email on a day-to-day basis. That's such a university skill. You need to be communicating with the outside world. And it's not text and Facebook and Snapchat and Instagram that you're using. When you get to university, a professional community is going to involve email. So please check that email. I'm probably emailing you at least once a week, maybe twice. Shoot me back some questions. Snap a photo to ask me questions. Make a list of things to ask me. Rewatch the video. Rewind it. I mean, you can watch it again in fast forward motion if you want. Some people run it at 1.5 times speed. So anyways, I'll stop the video. And yeah, hopefully that made sense. Ask me questions.